Here's a ball which is moving back and forth in simple harmonic motion. And like other simple harmonic motion we've seen, the ball is moving side to side. It's going in a sinusoidal motion. But actually, there's more to the story. If we zoom out, you can see what's really happening is this. The ball is on a turntable. So the ball is actually going in a circle. But a front view of the ball moving in a circle looks just like a ball moving in simple harmonic motion. Thinking about the connection between circular motion and simple harmonic motion allows us to say things about the maximum velocity and the maximum acceleration. And there's a table in a book that shows you the details of these connections. And that's useful information. Well, another piece of the story is to look at the energy in simple harmonic motion. And if we look at the energy in simple harmonic motion, we can say something about what are the physical properties that determine the frequency or the period. Now here's one thing that the frequency and the period of simple harmonic motion does not depend upon, and that's the amplitude. If I have this mass on a spring at a small amplitude, it oscillates with a certain frequency. If I pull it down to a larger amplitude and let it go, it oscillates farther, it oscillates faster, but it oscillates with exactly the same frequency. So it's determined by physical properties of the system. It's determined by physical properties of the system. And what determines it is two things: the stiffness of the spring and the mass that's oscillating. Now, I'm going to ask you some questions about this, because you can figure out how this should be affected. Suppose I took this mass on a spring system and I increased the mass. And I'll do this as I did previously by taking the mouse and giving it something to hold. If I take this and increase the mass, how will that change the frequency? We'll give you some choices. If we increase the mass, but we keep the spring force the same, it's a larger mass, but it's the same force. And so we'll have a lower acceleration. And so what happens is each oscillation is just going to take more time. And so it's going to oscillate with a longer period, with a lower frequency. And we can see this. If you have a stiff spring or a small mass, this gives a high frequency. If it's a relatively soft spring or a high mass, this gives a low frequency. How about a pendulum? First off, we're going to start with a question. If I pull the pendulum to the side, it swings back and forth in simple harmonic motion. Let's think about this. If I was to change the mass that's swinging from the pendulum, how would that affect the frequency? And think about this. What's the force that's pulling the pendulum back towards its equilibrium position? It's gravity. It's the weight force. And we know something about how things fall when the only force that's acting is the weight force. We use that as a hint. Question: if I take the mass of this pendulum and I double it, how will that affect the frequency at which it swings? We'll give you some choices. And let's give it a try. If I take this, swing it back and forth, there's the frequency. Now if I take it and add some mass, and I can do that the same way I did it before by putting a bolt in here, swing it back and forth, and what we find is it's the same frequency. It's the same period. The mass doesn't make any difference. And that's because this is just like free fall. The force that's providing the restoring force is gravity. Bigger mass, bigger restoring force. But the mass also provides the inertia. So bigger mass, there's more inertia. As a consequence, the acceleration and therefore the frequency and the period do not depend upon the mass. The only two properties that matter are the length of the string and the strength of local gravity. Those are the things that matter, which is why a pendulum is a great basis for a timekeeping system, because the mass, which is actually pretty hard to measure accurately, doesn't make any difference. What makes a difference is the length, and lengths are easy to measure accurately. So the first most accurate clocks were pendulum clocks. Now, when you let a pendulum swing, at some point it will slow down and stop unless you feed energy into it. And that is the basis for two more properties of oscillating systems, which we'll talk about in the next segment.